For the first ever TSConf, we were able to get a very special guest speaker. He was born in Denmark, studied at the Danish Technical Institute, and has been programming since 1978. He started working on an HP 2100 with 32K of Ferrite core memory and a paper tape reader and puncher. But he later upgraded to a 14-inch 1 megabyte hard drive. It's very fancy. His professional focus has been on programming languages and development tools, including Turbo Pascal, Delphi, and C#. And of course, you know him as the architect of TypeScript. Ladies and gentlemen, please welcome to the stage, Anders Hejlsberg.
All right, good morning, everyone. I'm Anders Hejlsberg. I am a technical fellow at Microsoft. I've been in the industry for an awful long time. As you heard, there probably about 35 years. I've been at Microsoft for 22 years and have worked on the TypeScript project probably for the last 7 or 8 years or so. Now, before I get going on my talk here, I want to give a big shout out, thank you to the SitePen organizers of this conference. If it wasn't for them, we wouldn't be here today. But also thank you to you, the community, for your tremendous support of our endeavor here. You know, it's such a wonderful product to work on because we're so close to the community and customers at all times. So thank you to all of you. Now, you may have seen this slide before. You know, TypeScript, it's about making JavaScript scale. Someone wrote a blog post recently, TypeScript, it's JavaScript with superpowers, you know, and that's in a sense very true to our core mission. You know, it's all about making JavaScript better. It's not about replacing JavaScript or embracing and extending, you know, it's about making it a better experience, more productive for everyone. I thought I'd start my talk with a little history about how we got there, because it is sort of an interesting story. And it takes us back to late 2010, early 2011, which were the first sort of rumblings of getting going. And back then, the world looked very different, right? 45% of web traffic went through Internet Explorer still. CoffeeScript was this new cool thing that the cool kids were doing. You know, jQuery ran the world. Knockout was dominating the server. Only 1 in 3 Americans had a smartphone at that time. ECMAScript 5 had just happened. The ES, after a 10-year pause, there was literally 10 years between ES3 and ES5, and then sort of this wasteland, and ES4 that got canned, and then the committee finally restarted, got ES5 out, and started to build momentum. And we were sort of right at the cusp of this momentum, and certainly we were seeing a shift in the world from the previously homogeneous, you know, everything is Windows, to a shift towards mobile now, and we could all see the future coming, you know, that this was going to be a heterogeneous world. This was going to be multiple platforms, different form factors, and cross-platform, therefore, was becoming increasingly important, right? And we were seeing teams both inside and outside of Microsoft starting to build really large JavaScript apps. A, because of what I just talked about, and B, also because Google, with their V8 JavaScript engine, and Microsoft with its Chakra engine, had probably at that point already gotten at least 10x perf improvement over your traditional browser. And we saw another 10x. We're literally today sitting at 100x perf of the original scripting engines that we had sort of in your classical browsers. And all of a sudden, it was actually becoming possible with that, the perf, the evolution of HTML, the evolution of the language, to write real apps in the browser. And it was also becoming a necessity. And so we were hearing from teams inside and outside, you know, that, boy, writing large JavaScript apps, it's hard. It is really hard. And as they get bigger, it gets harder. Because, you know, the language was never intended for this size apps. And the language at that time didn't have classes or modules or anything. It didn't have types either. And we knew from experience that the thing that powers the intelligent IDEs that we all want is types, statement completion, refactoring, go to definition, code navigation. All of that stuff would not be possible if it wasn't for the ability for some system to reason about your code. And you can't reason about the code if the code doesn't actually tell you what it's going to do until you run it, right? So those were all sort of the things that were going around in our heads. So we got started on this Strata project. Here's like, I actually went back. We have this OneNote that we kept our design notes in, and I went back and dug out some of the old ones. And it's kind of funny to see how even back then we were sort of pretty clear on what we were going to do. Let me try and see if I can get the highlighter to work here. We were to, oops, nope. Okay, that's going to be hard. Oh yeah, actually I hit it there. Be the most productive language, be faster than, that's an interesting one, I'll talk about that. Support excellent tooling, and all JavaScript is, yes, we were sort of like 3 out of 4. We had this interesting idea too, that maybe through types we could make performance better. Which is still an idea that's sort of going around. There's been this project called, I think it was called SafeScript or SoundScript or whatever. The V8 team at Google was experimenting with type-guided optimizations. But the reality is that the VMs are actually incredibly good at picking up type hints from the code and monitoring and choosing the golden path and good object layout. So that ended up not really being where we were going. Early on in the type system, we had like ideas like maybe we should, number. There's only numbers in JavaScript. Surely we can do better by having ints. So we must have ints, or we thought, and then we. We had interesting syntax, like you could see down here, for example, where we had the type in front of the variables. We used like C-style, typecasts, and for classes, recall here that there were no classes in JavaScript at this time. In fact, the ECMAScript committee haven't even begun to settle on a proposal, and early on we invented our own class syntax, which in some ways, I lament didn't end up being the one because it had this interesting take on classes just being functions, which they are. They're just constructor functions, right? So imagine that the body of your class is actually the function body, and that methods you declare in there get attached to the prototype or whatever. But you could actually put code in here. Then you could close over the parameters to the constructor and whatever. So it was an interesting but different model. And of course, once the ECMAScript committee ended up with a more Java-esque syntax, we switched to that. Some quotes from our early design notes. Is that yellow thing up there? God, okay. It's because it went into presenter mode. Let me just try to discard that and see if I can get it to not do presenter mode. I don't know if anyone knows about, let's see, slideshow. Here we go. Let's do that instead. Okay, and then let's go back. Much better. Now I'm seeing what you're seeing. Some quotes from the early design notes. This one I sort of still like because clearly it's worth the pain, at least to the users. I'm still not sure about compiler writers. I tell you, generics make your type system a heck of a lot harder. This one is subtle. 2 namespaces, a type namespace and a member namespace. It's one of those things that I don't know if you realize how we sort of overlaid the type namespace on the JavaScript value namespace. So when you import things with an import statement, you also get types, but they don't conflict with your JavaScript names. Like, it would be problematic if your types occupied the same namespace as your variables, right? Because now, all of a sudden, I can't declare it because there's already something in here by that name. But we actually overlay them in And then you sort of have the illusion of having these names, and then it depends on context. When you're in a type annotation, we look up in the type namespace. But when you're in an expression, we look up in the value namespace. And certain constructs inject names into both namespaces, like a class declaration injects a constructor function in the value namespace and a type in the type namespace. And it just sort of magically works out, and no one is confused. But it's actually pretty subtle what's going on there. I think early on we knew that there is no way we were going to appeal to JavaScript community if we built a closed. Could you imagine, like, if this was a closed source, you know, for money product? I mean, we would not be in this room. No one would have paid attention, right? So that insight was correct. And at the time, though, Microsoft was a very different company, you know, and the first couple of years there were some interesting discussions that we had with a lot of higher ups about, like, how do we get to where we need to be. What's the type of null? I'm still not quite sure what the type of null is, but I thought it was funny that we're still debating that one. And the old any type. You know, it's contagious, but it doesn't come out of nowhere, which is sort of like actually how any has panned out, right? And you know, we don't just inject any's, you know, and you can do no implicit any or whatever. So but it's still like a super important thing. And then finally, you know, this was always like, you know, whenever we started talking about, like, whenever you talk about type systems, it's like when it gets too advanced, it devolves to symbolic execution. And I thought it was funny because someone actually put up this issue not too long ago proving that TypeScript's type system is now Turing complete. You can literally write Turing machines. This little issue implements types that add and subtract and multiply numbers, and he's using compile time to compute numbers. It's crazy science, but the fact that you can do it does speak to how advanced the type system has gotten. All right, so we worked for a year or two, actually, and ended up shipping in October of 2012. And originally, we were hosted on Codeplex, which was Microsoft. This is part of the journey to open source, right? That's first, we got to put it in our own, we got to do our own processes. Here's actually a picture of us in Aarhus at the GoTo conference in 2012. That was the first public presentation about TypeScript. On your left there, that's Luke Hoban, me in the middle, and then Steve Luco, another technical fellow at Microsoft, who wrote the first prototype compiler, the 08 code base that we shipped at that time. That one was actually a port of our Chakra parser with a little bit of stuff added to it. But of course, we knew that wasn't going to be the real compiler, and so we set to work on TypeScript 09. And 09 was really sort of, we brought in some guys from the C# team, you know, who had worked on Roslyn and knew how to write compilers, and we proceeded to write a C# style compiler in JavaScript with lots of classes and auto-generated syntax trees and whatever, and oh my God, it got big in a hurry. But we also added generics to that compiler, and that was great, and that was a lot of pain. And we shipped that about a year later, but there were some perf issues with this particular code base. And I started to get curious, too, about this other style of JavaScript programming. You know, at the time, everyone was sort of coming at it from a very OOP-centric point of view, and I'll get back to that later in my talk, too. But I started looking at, hey, there's this other style, this more functional JavaScript, where you have functions within functions and closure, overstate, and whatever, where you're not actually using classes at all. And started writing a lightweight scanner, parser, type checker, and lo and behold, it turned out to be a heck of a lot faster and a heck of a lot smaller than basing it on classes. And eventually, we switched to that code base about a year later. Got 5x speed improvements and a lot of shrinkage in code. And that's the code base we're on today. So this is actually the third code base, interestingly. At that time, we also moved to GitHub, finally. Because Codeplex was kind of crickets, you know, and we were also at that point we switched to doing true open development. You know, it's funny, like open source for us was this journey, right? You start by thinking you know what open source is, and you lop the code over in a repo, and then you go back to your closed source practices, and then occasionally you scrape the issue tracker, put it into your internal bug tracking system, and but that's not the way it works, right? I mean, you gotta there's open source, and then there's open development. And this was really sort of the realization here that, hey, you gotta be where the action's at, and you gotta play the game the way the game is supposed to be played. And that was that genesis, you know, and that was that was almost 4 years ago now. And I would say at this point then, later that year, an interesting development happened. Google started talking about this thing called AppScript. I don't know if any of you remember AppScript. And we were like a little bit confused about it because they had TypeScript on their slide, and then they had an even bigger circle, and we were like, well, what's that then? And it turns out that was TypeScript with annotations and introspection, because they wanted runtime type information and decorators and whatever. We go, well, but we could do that in TypeScript. You know, why don't we come down and show you what we got? And then, you know, this is open source, right? We can think out of the box. And so we did. I remember going down in November of 14, I think, doing a couple of presentations at Google down in Mountain View, and we spent a whole day with the engineering team for Angular, and discovered that, heck, we're all just engineers, and we think about these problems the same way, and maybe we can do something together. And so we went back, we implemented decorators, because they promised us they'd give it a shot if we did, and lo and behold, not that much longer after, we actually saw Google switch to TypeScript for their Angular 2 effort. And I mean, in and of itself, at that time, at least, this headline was like kind of eye-popping, right? And that really gave us a massive boost also in credibility and in adoption. And I think at that point, we certainly now had found our stride, right? And these are sort of I'd say the 6 operating principles that have been the truth since, you know. Do open source and open development, closely track ECMAScript. And basically our rule of thumb there is that once a proposal reaches stage 3 in ECMAScript, we'll go implement it in TypeScript, because at that point we know with quite a high degree of certainty that it's going to happen. So we don't endeavor to create new statements or whatever in JavaScript. That's not our goal, or new statement level constructs. But we do endeavor to innovate in the type system. We sort of see that as our domain, right? So the type part of the syntax, we're going to innovate in. And we also endeavor to build best of breed tooling relentlessly, you know, and that's not just the language service, it's also IDEs, you know. How many of you use Visual Studio Code here? Wow, look at that. And thank you. And I don't know if you knew, but Visual Studio Code is written in TypeScript and was one of our earliest adopters. And we work really closely with Eric Gamma's team. And I have lots of respect for them. The other thing is, like, continually lower the barrier to entry, like a lot of the work that we've done with using TypeScript to power JavaScript. And I'll show you some of that later in the talk here. And then finally, to rephrase Steve Ballmer, community. You know, it's about community, and we fully realize that. And one good example of the power of community is definitely Typed, which sprung up very shortly after we released TypeScript. Did you know that last year, Definitely Typed was the most active project on GitHub? I mean, it beat them all. 42,000 commits from almost 6,000 committers. That's how busy it is. It's tremendous, like what energy goes into that. And we poured a lot of energy into building tooling around it. So we run a service that automatically scrapes. First of all, it automatically categorizes all the issues on Definitely Typed. It scrapes each of the packages up there, puts them in the @types namespace on NPM, publishes that. There's a whole bunch of infrastructure that we keep running to make it super easy for people to write these type declarations and just have them pop into NPM automatically. Another example is the work that we did in the latest release of TypeScript with Babel. We actually had one of our team members go work in the Babel code base to add support for parsing and throwing away, in a sense, TypeScript syntax, such that you can now use TypeScript as your type checker and Babel as your emitter. You simply run TS in no emit mode, and then you use Babel. And that means a lot of doors are now wide open in the React community, right? Because React is typically based on Babel because it comes with that tool stack. So that's another example of the power of community there. Brings us to today, and today surely is a good day. When I look at our NPM downloads, March will probably be the first month where we reach 10 million monthly downloads on NPM. And it's remarkable. You go back 3 years on this slide, we were at 5,000 monthly downloads, and now we're at 10 million. I don't even know how to think about these numbers. They're huge. If you zoom in on the last 2 years, you'll see that we have increased our release cadence a lot. We actually now try to release every 2 or 3 months. So there's always something new. It's hard to talk about the latest version of TypeScript because by the time you start talking, there's another one. And so we want to keep this cadence going. We also are religious about making sure that our nightly builds are good. So a lot of people run on. How many of you use TypeScript Add Next in your? A few. That's great. Thank you very much because that actually gives us super meaningful feedback. And we endeavor really hard to make sure that that's always good. We run all of our tests on it and so forth. RedMonk just last week came out with their programming language rankings. We are now tied with Go at number 14. We moved up three spots during the year, which is pretty cool. I think we're ahead of Swift, for example. One interesting statistic that someone told me was that last month there were more GitHub projects created for TypeScript than for C++. So we've definitely gotten into the big leagues, but we'll see how long we can sustain this. But it's wonderful. There was this Stack Overflow survey, and that was about the most loved, dreaded, or wanted languages, and we were actually the third most loved language on Stack Overflow, which I was real happy about. Lots of companies use us now, including the SitePen guys, GitHub, Reddit, Google, Slack, Lyft. It's great to see. I wanted to also show you a picture of the team. Not everyone was there. This was on Friday. We just decided to snap a team picture, bring it here. This is in our team room. There's about 20 of us, and we're in a single team room. And it's really wonderful because like everyone knows what's going on because just from the chatter in the room, right? And this team doesn't just do TypeScript. We also do all of our JavaScript tooling for Visual Studio, for Visual Studio Code, and so forth, and even some of the Node.js tools that we have. And a lot of the team is here today, and so if you see any of these people, please go talk to them, and we'll have a Q&A also with some of us later this afternoon. All right, so that's sort of my intro to where we're at. Now I want to talk a little bit about like how the sausage get made, and then like what's the engine of TypeScript. And of course, at the core of it all is a type system, and TypeScript has a very interesting type system. In many ways, unlike anything I've seen, over time, it's gotten more and more esoteric. It's a gradual and structural and generic type system, and it's really rare to see all of those combined. We have extensive type inference. We do control flow-based type analysis, which you all know from non-nullable types and whatever, and the ability for us to understand how flow of control changes, narrows the types in if blocks, for example. We have a bunch of novel type constructors, and I'll talk a little bit about those. And then, interestingly, we're both object-oriented and functional, which typically is sort of a religious, either you're one or the other. Now, speaking about the novel type constructors, Originally, TypeScript was just sort of a bunch of primitive types, and then the first one here on the slide, right? You could declare object types and function types, and that was sort of it. And then we've gradually grown downwards. Union types, got added, and then intersection types, and those really fundamentally change how you think about types, because now every root type is not just a single type; it is a set of disjoint possible types, and that brings about a whole different way of thinking. Instead of this single-rooted sort of OOP-like way of thinking of the world, you can think of the world as, oh, I can have a string here or an array of strings, and that's crucial to JavaScript. That is how JavaScript works, right? So that got us much closer to the truth. Key of and index access types, map types, and now the last one on the bottom is our new baby called conditional types. And these are in particular interesting because they only exist in higher order form, these types. So they are only ever there if one of the constituents is a type parameter. Like key of t, for example, the minute we know what t is, it evaporates and it just becomes a union of string literals, right? And t sub k evaporates and becomes whatever the type of that property is in that object, et cetera, et cetera. But increasingly, our work in designing the type system is actually about reasoning about these higher order type equivalences of all of these type constructors that we have introduced. And this sort of gets a little crazy now, but like here are some examples of, there are many of them, but for example, a union of t and the never type, which is the empty union, is just t, and an intersection of t and never is never. If you intersect two union types, you actually get a union of intersection types because unions distribute over intersections. Key of an intersection is the same as a union of the keys. This actually goes a way to mathematically explain why they're called union and intersection types and why people sometimes are confused. I've gotten this question a couple of times. People go, why are you calling union types, or sorry, intersection types, why are you calling them intersection types? Because if I intersect two types, I get a union of the property names, so shouldn't they be called union types? And well, no, because the words union and intersection speak to the sets of possible values of the types, the value domains, if you will. And when you create a union type, you are creating a union of the possible value domains. Imagine here's like all the possible values of string, and here are all the possible values of number, and string or number is both of them, right? Are all of the possible values you could have. Now, the thing that's interesting about object types actually is that the most encompassing object type is just curly curly. As you add property declarations to an object type, you are constraining the possible values, because you're saying this property is now always of this type. So all of the other possible objects where it was of other types fell out of your possible value domain. So you have these like infinitely large sets, but my infinite set is a little bit smaller than your infinite set, and you're actually constraining infinite sets. And that's why it's hard to think about, right? But that's why intersections are truly intersections, because they are less inclusive. Another interesting thing that we spend our time on a lot, it's like this is like your compiler writer's worst nightmare when it comes to structural types and generics, because once you combine those, you can create infinite types that are different in structure. Like when you compare two structural types, like say I have a foo and a bar here, right? For some t and u that so happen to be the same thing, but they're still different types. And now I got to see, are these two types identical? Well, oh, they're objects. Okay, well then we got to go look at the item property. Yes, they let's say it was foo of string and bar of string. Yep, they're both string. We're good there. Okay, now let's look at the next property. Well, in order to do that, we need to make a foo of string. Okay, and a bar of string. Well, they just got one bigger now. Oh, let's look at the item property of that. Yep, that's good. And let's look at the next property of that. Oh, foo of string. Oh, off we go to the races, right? And it's basically turtles all the way down, right? And and what do you do? What do you do? I mean, in fact, I remember we talked to some of the Microsoft research, like there's a famous person, Luca Cardelli from Italy, who worked on structural typing back in the 70s and the 80s, and is one of sort of the world-renowned experts on type theory. And then so great, he's at Microsoft Research, let's go talk to him. And he goes, oh, no one knows how to solve that problem. What do you mean? Well, and it turns out that all of the type systems that do structural typing, they cheat. And the way you cheat is you go, okay, well, I guess we'll just keep going, but then once we've seen enough of them, we just say, I've seen 5 now, and it seems to just keep on going. We're just going to stop here and say, let's assume it's true, and then let's check all the rest. And if that also turns out to be true, that's good enough. It's true. So we have the turtle cutoff. You know, it's about 5 turtles down. We kind of go, you know, we're going to stop here and call it true. It's funny, we got this far. We actually got, there was just in the last couple of months, there was finally a bug report that said, hey, I have this JSON document, and it's like 10 levels deep, and I noticed that if at the 7th level I made this mistake, I didn't actually hear about it, but, well, it's the turtle cutoff, you know, that's so. So we may have to increase that, but it's tricky. But these are some of the crazy things that we actually have to. This is where we spend our time in these crazy problems. Another one is strict. Strict is interesting because if you think about it, our job really, whenever you update to the latest TypeScript compiler, our job is to break your builds, right? No, that's what we deliver. We deliver error messages, right? And as we get better at checking your code, we deliver more error messages, and therefore we break your builds. And, well, that's a problem, right? So we can't be too strict, right? I mean, there has to be a way to control this strictness. And so in, I forget how many releases back it was, we introduced the strict flag. How many are you familiar with that and what it does? Strict basically sets the default for a whole family of flags. So now, the way we operate now is whenever we introduce some new type check that might break your code, like, for example, strict property initialization got put into 2.7, right? We put it under a flag. Now, you can choose either to opt in manually by not specifying strict, and then you can just, like, when you get a new release, it should still compile, and then if you want the new check, you can add that to your ever-growing set of strict things you opt into, right? Or you can go, no, I like pain. I want to be in House of Pain. You know, every time there's a new release, I want to hear about it because there might be a problem in my code. So you could actually run with --strict, which flips the default of all of these switches to on, and then you can explicitly opt out of the new ones. But you can try it first. So by default, you would try it, and then if it goes, oh, I'm not going to fix that now, then you can opt out of it. So we actually recommend that people do that, and if you say TSC-init, we put a strict :true in there. But that's the philosophy behind this, and that's sort of how we operate. All right, that gets me to I wanted to talk about like some of the new stuff too here. Conditional types is new, or it's gonna be new in 2.8. It's not out yet, and that's sort of, you know, our what we do here, in a sense, is as we think about where to go with the type system, is we're always trying to capture more ground of expressiveness, more ways of capturing patterns that actually occur in real JavaScript. So this is all, this isn't powered by, oh, this sounds interesting, let's go do that. It's powered by, hey, there's this piece of code there that I could not express, even though it is a mapping that is clearly regular and should be describable, right? And conditional types is sort of one of the last bastions that we haven't gotten to, which is, so far, all of our types have been uniform in structure. You know, even with map types, it's uniform mappings over type. Conditional types allow you to have non-uniform mappings, and they occur a lot in JavaScript. It's like, hey, if you give me a number, I'm going to go do this. But if you give me an array, then I'm going to go do that. Except if it's a string array, then I'm going to do this. You know, and that reflects then in the output, right? And how do you declare that? And that's really what conditional types are about, these non-uniform mappings. So here's an example, for example. Like, think of the type of operator in JavaScript. You say type of X, and today you're going to get string or number or Boolean or undefined or function or object. That's what we tell you. That's what it could be, right? But if we know something about X, we actually could know with more precision what the possible strings you could get back are, right? And so we could actually be a little bit smarter in that check. And so imagine that you declare a type name of T where you say, well, if T is a string, then it maps to string, the string literal type string, right? If it's number, then it goes to number, blah, 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 blah. Now, when you say type name of string, you get a string. If you say A, that's also a string. If you say string array, that's an object. If you give it a function, you get function, right? So now we're starting to reflect some of what happens in the type system. Now, but what if I give it a string or number? Well, it turns out that string or number does not inherit from string, nor does it extend number. It's the other way around, right? Yes, string derives or extends string or number, but not the other way around, right? And so for unions, we actually do this interesting thing that you saw me show earlier, which is we distribute over union types. So when you say type name of number or function returning number, we actually treat it as type name of number or with type name of the function returning number. And that gives you number or function, right? And so these become types that sort of you spread themselves over your union types and apply themselves to each of the constituents, right? And that turns out to be super useful, in fact. But let's first look at what it looks like in use. Let's just say I declared now a function called type of T that returns type of X now as a type name of T. Now in my code, when I write here, I have a foo that takes an X that can either be a string or a string array or undefined, or a Y that can be a number or a function returning number. Now when I say Tx is type of X, I get string or object or undefined. And if I now have an if statement where I try to compare that to function, you're going to get an error saying this could never be a function. You're wasting your time here. You know, so already you can see how this is useful, right? But here's where it starts to become really interesting. You can declare these types that reduce or filter your union types. So for example, here's an exclude and an extract function. You give it two types, and it gets rid of all the u-likes in T or extracts all the u-likes from T. So let me show you some examples here. Let's say I have A or B or C or D, and from that I exclude A or C or F. And then I get back B or D. Because we spread it over the union, right? And then if we evaluate to never, it goes away. Otherwise, you get T, then you keep it, right? Or vice versa for extract. And that's like useful, like let's say I have something that is of type string or number or function returning void or whatever, and I want to get rid of all the functions from that type. This is how you would do that. Or I want to extract all of the functions from that type. This is what you do with this guy. But notice how this is all built out of this one primitive, right? You can actually make new type operators yourself using these things, such as non-nullable. Get rid of null and undefined from my type. Now that one, everyone's asked for that one. So all of a sudden, this sort of fell in our laps, right? Here, non-nullable, string or number undefined is string or number because we just get rid of whatever parts of the union are not interesting. An additional capability we have in conditional types is the ability to infer constituent types. So imagine you want to write flatten, or maybe it's smushin of T. You could write it as, when T extends array of mumble, then I'd like to return the mumble, otherwise I'd like to return T, right? And now, if you give me a string, you get back string, but if you give me a string array, you get back string, because we fish it out of, and so we can actually sort of reach into types, fish out constituents, and return them to you. And you might go, well, where's that useful then? Well, how about return type of T? Now that's another one that everyone has asked for, right? How do I have a T, I want to get the return type of that t. How do I get that? Well, here's how you do it. You say when t extends a function taking any set of arguments and some return type, then give me that return type. Otherwise, just give me t. This turns out to be useful in the real world in, like, let's say I wrote a function foo that returns some insanely complicated type that got inferred and I don't even know how to write it down. Well, now I can just say return type of foo and obtain that type without having to explicitly write it down myself. So these are just sort of some of the interesting types you can do. Now, but as I said, you can use it to make your own type operators. So in lib.d.ts, we already have partial, read-only, pick, and record. I'm sure some of you have used those at times. And now in 2.8, there'll be 5 new ones. Well, 6 new ones, actually. There'll be a required of t that allows you to do the opposite of partial, which that's actually not related to conditional types, but a little extension to map types. But then we have exclude, extract, non-nullable, return type, and instance type that allows you to get the return type of functions and the return type of constructor functions and do funny transformations on union types. But for me, as a type system wonk, the beauty of this is that this is built out of just 4 novel type constructors, right? And we didn't have to put in like $this or $that built-in function or built-in type, you know, that only the type system knows how to write. It's all just, it just emerges out of these underlying quarks. That's always like, it's always fun to have that kind of beauty. All right. How am I doing on time here? Sort of okay. Let me try to show you a little bit of conditional types in action, actually, just because that is fire up code here. And look at one interesting example of conditional types that someone actually put up on the issue tracker, and it's how do I express the type that JSON.stringify returns? Let's say I persist an object as JSON and fetch it back. Do I get back exactly the same t? No, I don't, because certain things can't be JSONified. Well, how do I express that? Today, or before to it, you couldn't. It's just like, it is a non-uniform mapping. You know, there's no way that that's just one sort of thing that you do to everything, right? But it turns out that you could almost like read the ECMAScript spec now and put it down as a declarative type here. So to JSONify some t, the first thing that the runtime does is it says if t has a toJSON method, then take the return type of that and JSONify it. Otherwise, JSONify t itself. Okay? Now, in order to then JSONify a value, we say if you have a string or a number, a Boolean or null, you get the same thing. If you have a function, then they go away, because your functions cannot be put into JSON, right? If you have an array, then you get a JSONified array. If you have an object, you get a JSONified object. Otherwise, you get undefined. Now, to JSONify an array, you JSONify all of the elements, and then you turn undefineds into nulls. Now, don't ask me why, but this is what it does. Okay, so and to JSONify an object, you map over all the properties of the object and you JSONify each of them. And here it is in, what is this, like 15 lines? You know, we have declaratively described what JSONify does. And now let's look at whether it actually works. So here's some crazy item that has a text property and a number and whatever. And of course, if I hover here, it just shows me that you know, let's try to say item dot, for example, and see what do we get out of it here. Well, if we start with text, that just strings go straight through, and count, that goes straight through, and choice, that also goes straight through, but func became undefined. So if I try to call that function on something that's been JSONified, it's going to yell at me and go, you can't do that. That function's not there anymore, because it went away. Now, for nested objects, you'll note that we drill in. Let me try and scroll this up a little more. You'll see that nested has an is saved Boolean, and a data property. Whoops. So let's look at nested. And you'll see here that we have the Boolean property went straight through, but data, if we say data dot, you'll see that that became an array of 1 or 2 or 3 or null because the undefined became a null. Let's look at widget here. First of all, that's a nullable, but we can sort of drill into it with the banger operator and look at what happened to the date. Look at how widget has a date property of type date. But down here it's a string, and that's because date implements to JSON and turns dates into a string. So you actually get strings if you JSONify your dates. And likewise, your kind, since this widget implemented its own to JSON, you see that we've actually turned kind into this object type here. Or sorry, we've turned the widget into this object type, right? And then finally, with children, let's try to drill in, and then you'll see that it all actually does repeat. Sub-0, whatever, and we keep getting JSONifieds as we go down, right? So this is an example of like some really crazy stuff you can do, but it's not just nutty stuff either. This is like, and it's not necessarily something you yourself would use, but framework writers or writers of DTS files can put this to great use and capture the next level of expressiveness in their DTS files, and that will allow you to type check more and more, right? So that's really sort of what drives us here. Okay, let me go back to the deck. Talk a little bit about, well, I might skip this one. I don't know, how are we doing? Is that the correct time here? I have 10 minutes left. Someone yell yes or no? Yep, okay, all right. Okay, let me come back to this one if there's time. Talk a little bit about the work that we're doing to make the JavaScript experience better by using TypeScript. So I don't know if you all knew how we actually engineer the TypeScript compiler. We have a command line compiler called TSC. But then we also have this thing called TS Server, which is actually sort of a headless compiler that runs as an out-of-proc process that you can talk JSON to. And it's sort of the oracle that sits behind your editor. And it doesn't matter which editor it is, Vim, Emacs, Sublime, WebStorm, or VS Code, they all use the same language service. And all we write is a small plugin for that particular editor that can tell the TS server all of the things that's happening in your source code as you're editing. The user typed the character A, B, C in this file at this position, et cetera, et cetera. And then TS server keeps an in-memory image of everything you're doing. So it literally loads your project, parses up everything into ASTs, and incrementally updates them as you are typing in your editor. JSON messages are sent to that out-of-process guy, and it keeps up to date. And then the minute the user types dot, and now he wants statement completion, then boom, we're right there to deliver the answer because we've already computed it. And of course, we then endeavor really hard to only compute as little as possible at all times, right? Because we know from user UX studies that if statement completion takes more than 100 milliseconds, people get irritated. And so we full well know, even though you have 100,000 lines in your project, we need to deliver in 100 milliseconds or else people don't like it, you know. That's challenging when you're writing compilers. That's not what they teach you in school, you know. They teach you how to write command line batch compilers that have multiple passes and whatever. No. None of that works. So there's some interesting engineering in this compiler. But one of the things that's really interesting about it is that it doesn't just work on TypeScript. If you think about TypeScript is a superset of JavaScript, and therefore JavaScript is a subset of TypeScript, right? It is TypeScript without type annotations. But hey, that's fine. We can do inference. We can do lots of inference, in fact. So it sort of occurred to us, well, why don't we use TypeScript as the JavaScript language service? Because, I mean, my God, we can do all these fantastic things already. And that's actually what we've been doing now for the last year or so in Visual Studio Code. And so let me show you some of sort of the interesting effects of that. So let me actually, okay, here we are in an empty directory. Oops, okay. Now let me say npm install jQuery and Lodash. Okay, I'm going to do myself some JavaScript coding, and let me fire up code. All right. And let's try to make a main.js file here. And let's save that. And this particular build I have, I think I need to close and reopen it or else funny things happen. And now let me try $dot, and boom, statement completion. Where the heck did that come from, right? I mean, that actually, that actually came from the TypeScript language service. What happens here is that when you open up a JavaScript file, and we can first of all see, oh, you have some node modules installed here. Let's go consult the @types namespace on NPM. We do this in TS server out of asynchronous, right? Go look, see, oh yes, there are type declarations. Oh, let's suck them down and put them in some app cache for VS Code or for TypeScript, the language service that just sucks down all the type declarations. And now, when you're writing code, hey, if we found types, well then by all means, let's show you now. Now actually we can show you what all the crazy overloads on $.ajax are, for example, right? That otherwise you for sure wouldn't know. Let's try like Lodash.filter, for example. Well, that takes a collection here, so let's try to give it an array of numbers. And then let's try to write the callback. And now, notice how, whoops, there, x dot. Notice how we can now we can flow the types, we can give you statement completion on this. You never said anything about it, but we know this is the truth, right? So we can statement complete in unannotated JavaScript. Let's say I write a function foo of x comma y here, and then I say x dot. Well, yeah. There's not much we can do here, right? But, you know, a lot of people write JS doc annotations, right? So let's say x and y are strings, like that, for example. And now let's say x dot. Well, now, of course, we can pick that up and go with that, right? And so we automatically pick up JS doc annotations and run with them. Now, let's say I say return x times y. You go, what? I just said these are strings, and now what? Well, I suppose that might work, you know. I mean, if they contained numbers, right? But this is this is danger, right? Now, by default, we do not give you errors in JavaScript. So we power statement completion off of this stuff if we can, but we do not give you errors. We don't unnecessarily bother you. But if you really want us to give it a shot, then you can say add TSCheck at the beginning of your file. And now we'll type check. And now you'll see down here, this doesn't look good to us. You really ought to make that maybe you meant plus, right? Now the error goes away. And likewise up here, if you had misspelled a method, we can tell you that. Now, the thing that's interesting about this mode of type checking, though, it's a little bit different than how we type check TypeScript, because we need to be more conservative here. You know, in TypeScript, we're sort of that strict none there, right? We're gonna, like, if something could go wrong here, we're gonna snap you over the fingers there and let you know, and so now you gotta put an annotation or whatever. But in JavaScript, it's sort of the other way around, right? It's like, if it could be right, yeah, let it go. But in a lot of cases, we know this is never going to be right. So why don't we tell you about it? So we run the checker in a more lenient mode in JavaScript. But it's the same type checker. In fact, you can see an example of that if I say like let obj equals x:10 here. Right? And now I say obj.y equals 20. This is a pattern that occurs a lot in JavaScript, but TypeScript will give you an error here because it would infer the type to be x:number, and then it would say, oh, you're accessing a property that doesn't exist, which could also be true. I mean, who's to say? Did you mistype x and type y instead? Or did you mean to add another property? Well, so in JavaScript mode, we infer a more lenient type, right, where we say it's x:number, we know that much. But everything else, who knows? So you get to put whatever you want, right? Now, that's sort of just a brief idea of what we can do there. The last thing I want to show you here is some work we're doing to handle scalability. This is not for 2.8. This is probably more for 3.0, maybe, you know, or, yeah, you've always had like software projects. Software projects never get smaller. They only get bigger, right? Bigger, 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 bigger. And we actually, even though we endeavor super hard to keep TypeScript's performance at the same level, we have gotten a little bit slower because we check more things, right? And meanwhile, your projects have gotten a little bit bigger because you've written more code and nothing ever goes away. And eventually, eventually you get to a point where, you know, you have these 100 or 200,000 line single repo projects, right? And it hurts to open up that project, and you know, you may even run out of memory. And so, imagine, for example, you have a project that looks like this, right? Today, the way you would have to structure this, let me try the highlighter here, in order to get statement completion for, let's say you're working on the mobile part of the code base, you would actually have to set up a TSConf file that includes all of this stuff, or else you would not be able to get statement completion on everything and refactoring and whatever, right? And likewise, if you're working on the web side of your project, you would need to set up a project for this. So you get these overlapping projects, right? And now when you build them, then you're building the same artifact over and over, and your projects get really big when you're working on the leaf nodes because they fan out and they suck up all sorts of stuff that you weren't really planning to touch at all, but you still would like some statement completion on it and whatever, right? Now, you can structure your projects like this, for example. You could actually make each of these a separate project, and then you could compile that and produce a DTS file that you then consume in the next project up, right? But now, you don't get code navigation on that, you don't get automatic builds on that, you don't get watch mode on that, you don't get a whole lot of things that people have come to expect, right? So what we're looking at now is like, how can we make TypeScript better about this? An example, in fact, is the TypeScript compiler itself. Looks sort of like this. The point here is that at the core of it all is the largest component in the system, the compiler, and it's used by 5 different deliverables: the command line compiler, the server, the language services, the test harness, la-da-da-da-da. So when we build the largest component of our project 5 times over, you know, and it just keeps taking longer and longer. And so here's an example of what it would look like to structure that as sub-projects. And the feature that we're working on here we call composite projects. And it's the ability for projects to reference other projects. That's really in its simplest form. You know, a TSConf file can reference other TSConf files. And this is how the compiler would look if you structured it that way instead. And I can show you just sort of some metrics on what happens in a code base like this. So let me try to go to first the TS repo here. And then let me just try to say Jake clean. This is our existing repo. And then let me just say Jake here. Well, actually, let me fire up PowerShell. And then let's say measure. Command Jake. Host. Okay, so let's fire this one off, and it'll sit in the background and build, and it's going to take a while, so I'm going to go do something else meanwhile here, and we'll come back and see how long it took. Let me now go to another project I have, which is our experimental compiler, which is the restructured version of the compiler code base that also uses an experimental command line or experimental implementation of the compiler that supports composite projects. So if we look at the structure in here, we'll see that in the source folder we now have all of these sub-projects in here, and then at the very root we have a TSConf file here that produces nothing but references 6 other projects, right? So that's sort of where you start. And you just say, hey, I can just go in here and say, build this. And it will then in turn go, okay, I gotta like check that all of these guys are up to date. And if not, then I'm gonna go build those, right? And so let's try to look at, for example, the TSC project. So we'll go to source/TSC here. Whoops. Wait, what am I looking at here? Where am I at? TSCX source/TSC. Okay, and then let's look at its tsconfig.json. And you'll see the first thing it does is extends a config base. So let's try to open that one up. Config base. So I don't know if you knew, but tsconfig files can actually like inherit from each other. And so here's the base tsconfig file for everything now. And it says composite equals true for all of these projects. And when you say composite : true, it means that there are certain restrictions on we require that you must specify all the, in your tsconfig file, all the files that are part of this project, either by includes or excludes or the files list. So that we know what outputs get produced. So we can do a quick mapping from inputs to outputs as we do dependency checking. It's not a hardship, really. There's every project ought to do that, but sometimes you forget and the compiler still figures it out, and that's just the one thing that we don't permit. Now, TSC then, in turn, references the compiler. So if we open up that guy's tsconfig file, you'll see then that the compiler is a leaf node. It doesn't have any dependencies itself, but it references all of these files that it lists. And so here we have sort of a complete description of the structure of the project. And now we can do much better. Let's first go back actually and see, yes, it took about 2 minutes and 8 seconds to do the full build before. That's like enough to do sword battles and whatever. That's definitely not where we want to be, right? Let's try to go to this project instead, and let's try to do the same thing here. Fire a PowerShell, and then let's do measure command, and here we'll do a TSCX, and we'll force a rebuild. So this is sort of like a preview of what the command line compiler might be able to do in the future. And of course, we'll make this all available as services also that other build tools can use. And so you see first it's building the compiler. Then it's going to go build services. Server shared, blah, blah, blah. And eventually we'll get all the way through here, and let's see where we get. There, 30 seconds. So we already reduced it by a factor of 4, right? Thank you. Because we're not building the same thing over and over. Now, if we then try to maybe modify something, and then you'll see this is where it really starts to shine. Let's go to the compiler directory. Here, source compiler. Let's go to core.ts. And then let's just modify the version number of the compiler to include TSConf. Okay? So we save that one file. We go back to our command line here. Oh, that was the wrong one. Let's get rid of that guy. Let's go to this one here. And now let's try to measure command, and this time without a force rebuild, and we'll just let it incrementally build as much as needs to be built. And then you'll see it'll build the compiler, because we modified one of the files used by the compiler, and everything uses the compiler, but we didn't actually change anything in the external interface of the compiler. So the DTS file for the compiler didn't change. And that means upstream we go, oh, well, nothing changed here, so we're done. And so now we're down to 14 seconds, when you change a core component, and we can just incrementally rebuild just what you need to rebuild. And this all works in watch mode as well, so this is going to be a super cool thing. This is something we're working on for 3.0, and hopefully, now that the challenge with this is how do you do like go to definition and refactorings across multiple projects. That's where the headache starts, and we're gonna I can't promise you that we have all the solutions to that, like right out of the gate, but we're going to work it over time. All right, and now I better get off the stage here, I think. So let me just sort of summarize again with, let you look at our final slide. And just, I want to thank you all for being here. I don't think there's time for Q&A right now, but we do have a Q&A with the TypeScript team at the end of the conference this afternoon. I'm going to be there. A bunch of the team members are going to be there. And we'd love to take all your questions then. So thank you very much, and enjoy the day. All right. Thank you.